So Igor Carron has a diploma engineer from INPG, and then he went to the US and got a PhD from Texas A&M University. And after that, he has held several positions in nuclear and aerospace engineering. He was always interested in many topics, including mathematics and particularly compressed sensing. He has been writing the recognized blog called Nuit Blanche on the theme of compressing sensing for a few years. And also he created a Paris machine learning group with more than 8,000 members and more than 100 meetups in the region of Paris. And finally, in 2016, he co-founded LightOn, the company, with several others. And he's now the CEO of this company. And I suppose you will talk to us about what LightOn does. And you now have the floor. Thank you.
Well, thank you very much, Gilles. And thank you for the introduction. Thank you for the organizer for having me for this presentation. I've got about 30 minutes. I'll try to explain a little bit what we do at LightOn, and hopefully I'll try to get to be answering a few questions, but if you can't ask your questions, don't hesitate to get in touch with us through emails and everything to make sure that it does so. All right, so let me share my full screen. You should be able to see I'm going through the panorama. And so the subject of the talk today is going to be about, let me try to remove my face from here because I can't see everything. Computing AI with Light. LightOn was created with 4 co-founders. I'm one of them. The 3 other co-founders are Laurent Daudet, Sylvain Gigant, and Florent Jean-Cléa. And out of the 4 co-founders, we all have 4 PhDs, except 3 of them are physics professors, and I'm not one of them. So let's get on to discussing why we're talking about AI and light. So what has happened in the past year has been earth-shattering on many respects. One of the big news of the last year is not really the COVID, it's really what happened back in June by the release of GPT-3 model by OpenAI. It's a startup company back in the US, in California. And they have been able to build one of the largest language models ever. And what is very interesting is they've gone through several iterations of these models. But this is the first time we get to see that now it gets to have something that we as humans consider something like getting to understand a little bit the context of what is being spoken when you are interacting with that system. And so to give you a simple example, because there are many of them on the internet, I'd like to essentially just point out one of these outputs. This is a small GIF of sorts that essentially outputs whatever you're asking the model while you have been training the model, while you haven't been training the model on anything, really. You have been training the model on a very large amount of data. Some of this data includes some of the codes, the language that you're using to do some coding, and some of them includes Keras and other type of languages. And so when you are asking this model to essentially write a computer code based on the specification that you're giving through the text, see what happens. So this is the model you want. And you're basically asking the model to take this sentence and give you an answer to that. And this is the answer. What's absolutely fascinating here is that to a very large extent, we're beginning to see the first time where we do not have to specifically train a model on a specific task. We get to be learning different tasks, mostly because now these models are getting better and better at the context of what the request is. So what is really happening nowadays is really that there is a race going on. That is, GPT-3 is just one step. The next step is really getting to have it bigger. And the underlying reason for it is mostly that when you're looking at these language models and other models that are multimodal eventually, is that you're getting better and better performances as soon as you're getting bigger and bigger models. And so when GPT-3 at 175 billion parameters, you are expecting to have better performances with something that has 10 times more parameters, or sometimes that has something that has about 1,000 times more models. And really the main problem really is that you're getting to the point where even though now if you get to be able to train those models, you get to have an accuracy that is much beyond what you have been able to see before in computer science. But the main problem is really that you have to probably have a different type of hardware to do all these things. So one of the ways for people in over OpenAI, but also Baidu and other entities are looking at this and say, well, out of all these computing experiments that we do, are there any specific rules that we can get out of this? And sure enough, what we're getting to see nowadays is the appearance of what we call scaling laws. To a very large extent, it's basically a lot of computations being done and how to empirically fit the behavior of the overall system so that eventually you get to have larger and larger models, but you get to know exactly why each of the parameters need to be used in a certain way. And as you can see on the right side at the bottom, you're beginning to have very empirical-ish type of ways to figure out exactly how the loss of your function is going to be. Because it's now going to be a function of different parameters with a certain exponent, everything that is absolutely empirical, but this is absolutely needed to essentially go a little bit further, because these models being so huge, you don't get to have that many computing training capabilities, and you don't get to be training that many that often. But what's very fascinating here is if we've been here before, we've been on this territory before. Back in 1920s, 1930, you could see that people were very much concerned about getting to understand how heat transfer was going on, how fluid mechanics was going on, so that you could build better cars, you could build better power plants, you could build better electrification systems. And so by having this whole need from the industrial base for some type of law so that you could be designing those things, people have been coming up with very similar type of scaling laws based on essentially dimensionless numbers coming out of physics, where you, instead of having numbers like the number of iterations like we see in these models for GPT-3 and so forth, you get to be looking at specifically the velocity, the type of temperatures, and any type of the components that you have in the liquids to essentially figure those things out. What's also absolutely interesting here is that the parallel is very, it's taking you aback when you look back at this, because you get to see that most of the engineering that we know, most of the engineering that is on which we are living on today, is absolutely dependent on these scaling laws. That is, up until very recently, we could essentially do much better simulations on HPCs, but a large part of the engineering that on which we live today is basically based on these scaling laws. And so back in 2020, we get to be able to see people that are doing absolutely magnificent type of simulations on high performance computing, mostly based on a keen understanding of some of these Navier-Stokes equations and so forth. But deep down, a lot of these empirical laws still subside, and you get to be able to even see those things, mostly because at the very beginning we were able to build those things from these scaling laws. And so what is really, if I were to be taking a parallel with regard to what we see in the AI these days, we need to be able to see what has happened in this whole heat transfer and fluid mechanics type of deal for the past 100 years. And so to get to the stage where we have these very good looking type of simulations, we needed to have three ingredients. One of them is the need. What you see here is the number of cars that were built after 1900, and you get to see two bumps. One of them is the 1929 crisis, and the other one is World War II. But from there on, you can see that the need is there. Everybody wants to have a car, and everyone wants to have a car that goes faster. Everybody wants to have a car that is also better designed and also can be much safer as we go along. The second ingredient is really how do we go about doing those computations? And one of the ways to do this is to do computing at a massive scale. And HPC, high performance computing, has been doing that for the past 30 years, really, a bit more, but really for the case of doing fluid dynamics and heat transfer, it's been there for about 30 years. And really it's been in the acceptance level only in about 10 years in those industries that really need to do those things like transportations and so forth. And this third thing is really the algorithm. And you know, when you're looking at all the other algorithms that have been developed in the past 100 years, most of them have been there mostly as a way to make sure that computing hardware would essentially be doing well in terms of what those simulations would be doing. And so now we have to go back to what are those three ingredients for AI in 2020s. What is the need? And so a lot of people would say, you know, AI is needed or not, or it's ethical and everything. All these things are very good questions. But what we see now at LightOn and many other outfits is really that there is a push for getting those very large models. NVIDIA just came out with a prediction that in about 5 years, that's 5 years from now, 2026, 2025, we ought to be seeing at least one client who would be willing to pay for one model for about $1 billion. Training one model for $1 billion. $1 billion with a B. What is the computing hardware? We think it's going to be HPC plus something else. And what are going to be the algorithm? What is going to be the algorithm that we know plus others, obviously. But the main problem with the hardware we see that nowadays, especially for the training, is that even though Moore's law is still going on, probably not at the same pace as we're being accustomed to, it's not going as fast as what the models require. The massive effort that you see in the training for these large models occupies a whole data center. GPT-3 requires 1,000 type of GPUs for a few months to essentially get it to be trained. And so if you're looking at GPT-4, 5, and 6, you're multiplying by 10 every time, and you see the sheer size of the needs that are going on there. And not just the sheer size, but the sheer size essentially also tells you that you need to have different type of algorithm, because otherwise you're not going to be able to have more HPCs. Those HPCs need to be wired in a way that allows those algorithms to actually work efficiently, or allow for the GPUs or the CPUs that are being run to be fully utilized. And if you do not have the right algorithm, you basically are not spending, you're spending about 80% of the time for the GPU or the CPU to be doing nothing and waiting for information. One of the very interesting insight is that one by Sarah Hawker on the hardware lottery. I invite you to take a look at it. It's very insightful. It's essentially how do we go about choosing the tooling and the research ideas that are succeeding or failing, and how do we do this when we have a certain type of hardware. And the hardware lottery is really about making the fact that sometimes some algorithms are doing much better than others, mostly because they're working on specific hardware. As soon as you're changing the hardware, you really need to have the right algorithm that fits into this. Otherwise, it's just hardware, and no one's going to be interested in what you have to say besides building it, and if anyone wants it. And so at LightOn, we've been looking at this from this perspective. That is, you cannot do a hardware without doing AI, and you cannot do AI without doing the hardware. And so we've been looking at this training of hardware beyond what we call backpropagation, which is the workhorse of deep learning these days. And we've been looking at half of the company at LightOn is mostly an AI team that has been looking at these novel AI, novel training methods that are going beyond backpropagation. And eventually, how do we go about having a dedicated hardware when you know everything about the algorithm itself? If you know a bit about backpropagation, which, as I said, is the workhorse of how you train those algorithms, you know that it's fundamentally a sequential process. The thing of it is the data has to go through each of the layers. The computations are matrix vector multiplications, and then you have some nonlinearities, and then eventually you go on to the next one. And then when you have a result at the very end, what you want to do is do the actual learning, and the actual learning is making sure that you compute the loss, you basically compute the gradients, and you essentially forward backwards into the process, and you go layer by layer. And that process is being sequential, and there is no way around it. There is no other way to essentially train those very large algorithms. So at LightOn, we've been looking at different algorithms. One of them is called direct feedback alignment. It came out from someone who wrote about it and published about it in Europe in 2016 on the fact that there is potentially a possibility of, in the backward path of the training of algorithm, to go potentially embarrassingly parallel, as we call it in HPC. The point of it is you still go for the forward methods of essentially getting your data from one layer to the other. And then eventually, when you are at the output, instead of taking the loss and distributing it to the layer that was before all the way to and sequentially backwards, you essentially give out that loss and you multiply it by a random matrix. You do a random projection on that loss, and you distribute it directly to each of the layers, all at the same time. And by the same token, you essentially remove this whole sequential process and you make it a wholly parallelized one. And one of the things that I would like to point out is really that it's by no means something that is obvious. When you're looking at random projections, you're really looking at something that is of the order in mathematics, since we are at the colloquium about mathematics today, we're talking about understanding random projections, and a lot of it comes from compressive sensing and earlier by Johnson and Lindenstrauss back in '84. But the point of it is that even using random projections here, for those people that know about random projection, is still a bit not explained at all. And so we're looking forward for anyone to explain to us a bit why it works so well, but I'll get to that a little bit later. The point of it is, when you are changing this algorithm to be going from a sequential to a parallel one, you get to be saving a lot of time, and you get to be able to make sure that the GPUs that are in each of the layers get to be used more efficiently. And so DFA, this direct feedback alignment, scales to modern deep learning tasks and architectures. And so we've been showing that at the latest NeurIPS conference, where we showed that it actually works for graph convolutional neural networks, as well as neural scenes that with modeling with one of these algorithms called NERF, as well as hybrid transformers. Main limitation is really that you have to fight backpropagation and backpropagation has essentially been optimized in the past 20, 30, 40 years, whereas we're just looking at this model here, at this algorithm, and it really does not have that much history, and it really does not have that much theoretical understanding, but it still works. And in computer science, you get to see that whenever that works, it's good enough. A little bit like the engineers back in the 1930s when they were designing those heat transfer for the radiators of cars. The other interesting thing is that you can also do hybrid strategies of DFAs and backpropagation at the same time. And most of the important part is that since it works on all these architectures, it's architecture agnostic. And that's one of the very interesting part of this story. And so now we have to fit this back into, okay, how do we go about doing random projection for to be able to actually implement this DFA in training those very large networks? And so in order to do random projection, which is a multiplication of a very large random matrix with a vector of data, you have to do several things. You have to generate lots of random numbers. You have to store them in the matrix, and then you have to do the matrix multiplication that you would be doing on CPU and GPU. And so, as I'm pointing out here, this process is neither fast nor scalable using current silicon. And one of the ways we've been looking at this is leveraging the physics of light and how light interacts with diffusing media as a way to get this process done. And so what you get to see here are two different things. So first of all, on top, you get to see that you have an X, which is essentially about to be multiplied by a matrix. I realize that this is the wrong notation for mathematicians, but in machine learning, they get to be using different notations. I think it's on purpose to make sure that mathematicians are not coming up to them and explaining them the word. But the point of it here is you get to multiply this H by X and you get Y. X is a bunch of vectors, is a vector with that can be represented on what we call a spatial light modulator. And then you shine a laser on the spatial light modulator and you basically make it go through what this this diffusive medium that is here in the black part here. And then when the light comes out of here, of that diffusive medium, it gets to be picked up by the camera, and the camera essentially is this Y vector. And so let me show you what happens when you're shining a laser through a diffusive medium. You get to see that light interfere with each other, with itself through the whole medium. And this is one with few elements. But what you get to see on the camera is this whole interaction of all these interferences with each other. Interestingly speaking, what that means is we're capable of having about a vector of about 1 million size, a vector that is about 1 million size, and you get to have as an answer a vector Y that is about the same size, about 1 million, and you have the matrix equivalent of about 10 to the power 12 random coefficients. It's actually 2 to 10 to the power 12 because those are complex random coefficients. So it's easily equivalent to several terabytes of memory. We get to be doing this at several kilohertz, so it's not just a once in a while type thing. It's mostly making sure that we get to be able to do these computations at a peta-ops type of scale. And in order to do all this, we need to use about a few watts, few tens of watts. Let me recall to you what a GPU currently uses. It's about 250 watts. And it cannot do several kilohertz of data of the types that I'm mentioning here. So given all this, at LightOn, we've been essentially building these OPUs that are doing random projections, and we've been using it to demonstrate it for a diversity of a set of use cases. You need to go to our blog to essentially see how it's being used. It's been used for detections of changes, a change detection type of data, as well as reinforcement learning, all the way to some more traditional supervised learning. And it's available on the cloud. Also, the fact is free space is bulky, is generally something that comes out of physicists when you're expecting them to do their experiments on the large table that doesn't move anything. We get to be able to do this in our next generation at about the size that could fit onto a PCB board. Eventually, what I'm trying to tell you here is that we've been doing this random projection optically, and we've been able to show that it's actually doing well on a diversity of model architectures, and it scales past some of the largest models that were computed in the past. We've been using it on NIST. In the first place, that's one of the first data set that you want to see. But then eventually we looked at graph convolutional type of systems, and then eventually a toy GPT model. But I'll get to these results a little bit later in the year. As you can see, when you get to be able to see what the DFA, the optical DFA does compared to backpropagation done on silicon, the differentiation of features is pretty similar to what you would be able to get in both technologies. One of the things that happened yesterday is really that you can get your own OPU in your own data center as of yesterday. Up until now, we had a scheme where people could actually use our technology directly on LightOn Cloud, where we have 4 or 5 now OPUs. Now you can get yours in your own data centers. And one more thing, we're not just looking at training optical networks. We're looking at building optical transformers. And eventually, in about a year from now, we ought to be looking at proving there is an optical advantage in using OptiU LightOn's technology to build massive models. All this wouldn't have been be able to be told without the 19 people that are working at LightOn so far. As I said, we are mostly a hardware company with an AI company, both talking to each other every day. And we have had our technology running for about years now. And we're kind of looking for the next step in making sure that the next generation of computing gets to have our technology. That's it. Thank you.
Thank you a lot, Igor, for your presentation. So we do have a couple of questions. Maybe there is a question about reproducibility. So I guess what I interpret the question as is, so in traditional random number generators, you can reproduce them using a seed. And here, is it possible using your technology? Is that a problem? Can you reproduce some results?
Yes. The issue at hand here is making sure that the matrix gets to be staying the same over time. And so part of the engineering that goes into the OPU is making sure that the matrix stays the same. It's not a random matrix that changes over time. It comes from the same, each coefficients are essentially coming out of a specific distribution of a Gaussian distribution. But the point of it is, as soon as they are there, they stay there. It's not something that changes over time.
So do I understand correctly that each of your OPUs basically contains a fixed random projection matrix?
Absolutely, absolutely.
Okay, but of very, of course, huge size, but
it's actually very large. That's the main thing. Yeah. Is if you were to be using a von Neumann type of a silicon chip that would be able to do these computations, you would see that you would be spending a lot of time doing the memory swap between the RAM and the actual compute to essentially get these computations done. So what we're essentially providing here as a thought experiment in a way is basically that in the future we're kind of expecting that a lot of the computing is going to be in 2 ways. There's going to be the computing that we know already that can be done using the von Neumann architecture, where you essentially have to permute the memory pretty often to get computations done. And there are a certain amount of memory where you don't really need to change the coefficients as much, where the fixed coefficients are good enough. And this has been shown in compressive sensing to a very large extent. That is, you could see that using just the same random projection was good enough to essentially get into going beyond what you would be expecting from Shannon's theorem for signal processing. So to a very large extent, the fact is, if you get to be able to do these computations for free, like you can on the OPU, a lot of the algorithms that you can use are changing, and that's liberating, because a lot of the paper we get to see when people are using random projection is trying to remove the random part and try to change them with sparse approximation of them. It's fun and dandy, but the problem is that eventually you get to be spending the whole paper on how you replace the dense projection, the dense random projection into a sparse random projection, without going the next step as to why it is useful for other purposes than just approximating the dense random projection. So it's, in French, I'm calling it very often la stratégie du contournement by most of the researchers, trying to essentially go around things that are very difficult to compute and eventually trying to find a way. But at that point, they don't have that many people that follow them, and they will not get that many citations. So a little bit like what Sarah said in her hardware lottery essay. If you give people, to a very large extent, a new type of hardware that does things that are very difficult to do on silicon chips, kind of thing, you are essentially opening the door for much more creativity in new algorithm. And one of the things I presented today to you is really coming out of that. That is, the creativity of us looking at DFA has been mostly because we knew how to do random projections in the first place. And to a very large extent, you cannot investigate DFA if you do not have these very large size matrices. If you see some of the papers talking about DFA in Scholar, you get to be able to see people that are essentially saying that it doesn't work at too large of a scale, mostly because they do not have the resources to actually do this computation themselves. And so what I'm really trying to say is that the tool itself changes the algorithm, and the algorithm changes the tool. And so that's a bit what I was trying to point out here today and show you what we do at LightOn.
And so maybe to just a follow up, to confirm, because I got a lot, some questions also on that topic. So what an OPU is absolutely not something like a random number generator. It has this fixed matrix, and it is really something which is can considered a random projection, but with the same matrix over and over again. So it is completely different from a.
And you know, if someone comes with a huge case where those coefficients need to be moving, I'm sure half the company here at LightOn will be embracing that new algorithm that essentially requires those matrices to change, and we'll make sure that those matrices are changing at a rate that cannot be sustained in silicon.
Someone was actually asking about other applications like two massive Monte Carlo methods in that direction.
Yeah, I think one of the Monte Carlo way of looking at this has been in machine learning has been using random features. When you take a look at this paper from Resh and Rahimi back in 2007, you get to see that they actually need those random projections to be there, and it really seems to acknowledge that those methods are very useful because they're essentially Monte Carlo approximation of kernels. Since it has received, I think the award of the time, I can't remember, the test of time type of award at New York's last year or the year before. It's mostly because people realize that in order to approximate some of these kernels and many other potentially other functions, you get to, the only way to access it is through a Monte Carlo type of techniques, like the ones they devised back in 2007.
And maybe one last question. So thank you for answers. So about how useful are mathematicians to you? Are you working half with mathematicians or rather other profiles? I mean, you yourself has a very broad profile. I mean, I understand that you are both a foot in mathematics and a foot in physics, or I don't know, but
I think what we generally require at LightOn is, well, first of all, as you probably have figured out, when I got together with three other co-founders, I tried to hire, I tried to get people that were smarter than me. And so my point of view is to always hire people that are smarter than me in some respect or another. And so getting a PhD in mathematics is definitely one way to go about this, because I don't have one. But the point of it is that we are not looking specifically at past work. We're looking at how curious people are. We currently have three PhD, three students that are doing their PhD within LightOn. Part of this presentation is actually part of one of these students' PhD thesis right now, and that person is essentially taking on some of the work that goes into this extreme scale type of training that we are pushing over at LightOn. So my point being that aside from a PhD per se, I'm much more interested in people that are curious and potentially much more smarter than me, but that's a different way of looking at it, but much more curious than other people. The main aspect of our work absolutely requires people to know what they don't know. We have to have a common language between people that are doing the hardware, people that are doing optics, because there are different kind, the mathematicians. We have to have a different kind of people when we're talking to integrated circuits and eventually some of the electronics integration. All this requires people that have seen very tough problems and try to essentially swim along those things. And so I think one of the things that comes out of doing a PhD in mathematics or other related fields is really that we know that people have been left alone for about 3 years or even 5 years in some other countries, and they've been able to actually push through and get out and essentially find out their voice to a certain extent. And so we're looking for this type of profiles because we know that they're the ones that are going to be bringing us the next use case or the next big thing that we want, on which we're going to be striving over at LightOn.
Thank you a lot, Igor. So I'm sorry I have to cut you because we are running a little bit late. So thank you a lot for our presentation and your comprehensive answers to the questions. So now we'll leave the place to the next speaker. Thank you a lot.
Thank you very much, and thank you for having me.